Continuing with section 2.3, the inverse matrix theorem. So remember, have the inverse matrix theorem in front of you, all the statements of that from, I think they are starting, there are 12 of them. So from A to L, because we need them to answer these questions. So we had started example 1, just to reiterate again, we had to mark true or false and justify our answers, assuming here that A is an n by n square matrix. And so because all the statements of the IMT are given for A as a square matrix of order n. So the first statement, if there is an n by n D matrix such that AD is equal to I, then DA is equal to I. So this is, you can say this is correct or true because of the statement right after the IMT, which says if A and B are square matrices such that A times B is equal to I, then A and B are both invertible with A inverse is equal to B and B inverse is equal to A. So here when we say D is an n by n matrix, now we already know that A is an n by n matrix. So they are both square matrices of the same order and AD is equal to I. Then each of them is inverse of each other. So we can have this statement. So you can say yes by true by statement after IMT. Okay, B part, if the linear transformation that maps x to ax, A times x, maps Rn to Rn, then the row reduced echelon form of A is I. Well, just read carefully. It says the transformation maps x to ax, maps Rn to Rn. So if you notice, we had two things, one to one and on to. Well, any map, any function can be a two function, like from set A to set B or set X to set Y, but on to and one to one, they are like special things. So in the statement of the IMT, if you look at I statement, the linear transformation maps Rn on to Rn. So then we can compare it with the part B, which is saying A is row equivalent to the n by n identity matrix. So if it is an onto map, then it will be A will be row equivalent to, or A can be reduced to an identity matrix in the row reduced echelon form. But here, because we don't have an onto map, so it will be false. Now, part C, if the columns of A are linearly independent, then the columns of A are span Rn. So this is true. And why? Because this statement is true. The first one is true because the IMT E, the E says the columns of A form a linearly independent set. So we are in this statement in IMT E, and then that gives us IMT H. So yes, this is true. Let's look at the next ones. Okay. Okay, so the next one is saying if the equation Ax is equal to B has at least one solution for each B in R. So this is in IMT, this is the G. This is the IMT G statement. And then it's saying then the transformation which maps x to ax is not 1 to 1. So we are going to compare it to the F statement. So in this statement or in this problem, they are stating that one of the IMT statement is true and the other one they are saying is false. So this means this statement is false. Because if we have the first situation that AX is equal to B has at least one solution for each B in Rn, then it must be a 1-to-1 statement, a 1-to-1 transformation. Part E, if there is a B in Rn, vector B in Rn such that the equation Ax is equal to B is consistent. So this is the same thing as has one solution, at least one solution for each B. So this is the same as IMTG. Then the solution is unique. Okay, solution is unique. So what does that mean? Solution is unique, that for every B in Rn we have one X from Rn which maps that X to the B. And this is true. Why? Because that means that is how we are getting our transformation 1-to-1. That transformation that maps X onto Ax which is equal to B. So in other words, the transformation that maps X to B, it has to be, it is 1-to-1 and it is onto, therefore this has unique solution. This will have unique solution. Or in other words, you can say, okay, because IMTG is being satisfied or it is true, so which means the A matrix has n pivots according to the C IMTC n pivots. So this implies A has n pivots. What does that mean? It means no free variables. So solution is unique. Okay. Let's look at problem number 2. Example 2, give brief answers. So first one, when is a square upper triangular matrix invertible? So remember, in an upper triangular matrix, the determinant is computed by multiplying the diagonal entries. And if the determinant is 0, the matrix will not be invertible, and if the determinant is non-zero, then it is invertible. So if you are taking the product of the diagonal entries, then it means the diagonal entries should be non-zero. So it will be invertible if or when all diagonal entries are non-zero. Okay, so same thing for the first and same thing for the second. All diagonal entries are non-zero. Okay, the next one, part C. If an n by n matrix A is invertible, then the columns of A transpose are linearly independent. Explain why. So you can connect this, that A is invertible. So according to IMT, A is invertible by IMT. A is invertible implies IMT E E that columns of A are linearly independent. So that's what IMTE is saying. And then if you look at is invertible also implies the IMT L, which is saying A transpose is invertible. So then by IMT E, so A transpose has linearly independent columns, or columns of A transpose are linearly independent. So these connectively linearly independent. Looking at the next part, if A is a 5 by 5 matrix and the equation AX is equal to B is consistent for each B in R5, is it possible that for some B, the equation AX is equal to B has more than one solution? Why or why not? Okay. So remember again, by IMT, if we have a 5 by 5 matrix, then the equation AX is equal to B is consistent for each B in R5, which means the statement G is true, that for each B we have a solution, or with the equation at least one solution. So the question is asking, can it have more than one solution? The problem is when the first statement is satisfied, so then the second, the other thing is that we have a you can say a transform T which maps X to AX, which means X to B, where T is 1 to 1 and on to. So if this equation has more than one solution, what it means is that the transformation is not 1 to 1. So if the transformation is not 1 to 1, then the equation, this cannot be happen. So for the first statement, so IMT G is true, which implies the T which maps X to AX is 1 to 1, but if AX is equal to B has more than one solution, then T is not 1 to 1. Therefore, that's why this is not correct. This is not true. Okay, so moving on. Okay, the next part is saying, explain why the columns of A square span, so there is an S missing here, span R2 whenever the columns of n by n A are linearly independent. So there is an A missing. I should just say of A are linearly independent. So if we have that columns of A are linearly independent, then the columns of A2 will span R2. That's what basically we have to show. So note here, from IMTA, columns are independent. We start here. The columns of A are independent, linearly independent. So columns of A are Li, linearly independent. This is from then. So this is kind of IMTA. So then IMTE is saying that, then IMTH is saying the columns of A are span Rn. IMTH, columns of A span Rn. So here the same thing, and now from the from IMTL, no, sorry, A square. So A square is just A times A. So A square is invertible. So if A is invertible, then A square is invertible. So following that, which implies columns of A square are Li, and which implies columns of A square span R2. Last part of this example, suppose a linear transformation T from Rn to Rn has the property that T of U is equal to T of V for some pair of distinct vectors U and V in Rn. Can T map Rn onto Rn? Why or why not? So the answer is no. You cannot have an onto map, and the reason is because T of U is equal to T of V when U is not equal to V. So remember, we have to have the bars on U and V because these are vectors. So when we have this situation, then T is not 1, 1. So if it is not 1 to 1, it means it is violating the IMTF. So if it is not 1 to 1, which implies T is not onto. Okay, I will stop here and then do the next example or next examples in the next video.